Hi, welcome to this video. My name is Phil and I'm a senior lecturer in astrophysics at the University of Lincoln. And again, I'm going back to galaxies again, but this time round I realised I actually haven't explained the central parts of galaxies. So what we will classify as the bulge, and there's a few different sorts of bulge that you can actually get. So I'm going to use this video to basically explain what the two types are and just give a basic overview of the main differences between the two. Now, if you haven't come across galaxies before, I'm going to give a real basic recap of the two main types. The reason why I'm going to do that is because they directly relate to the different sorts of bulges that you have as well. So it's quite useful to know anyway. So just to recap, galaxies are these enormous systems of stars, gas, dust, dark matter held together by gravity, so they're gravitationally bound. This particular one here is a disk-like galaxy, so it's kind of rotating like a disk. It's relatively flat. We classify that's kind of like flattened into a disk shape. Other ones are not, but they can have different ratios of stars, gas, dust, dark matter, but they all kind of contain some amounts of those. Others have more or less, but basically these are massive systems with a whole variety of different things in them. So they do come in a variety of different shapes and sizes. We can have disc-like galaxies, we can have more spherical ones like elliptical that are smooth, they don't have any spiral arms or anything. We can have irregular ones which don't have a regular shape. We can have dwarf galaxies, massive galaxies, and they all have slightly different properties. So they come in a whole variety of shapes and sizes, and actually so do the center regions, the central bulge of a galaxy as well. So to recap the different sorts of galaxies that we have, the two main types are spirals and ellipticals. Now spirals, on the Hubble classification system, tuning fork at least, they sit on the right hand side. You've got two branches there. So the top one is your normal spiral galaxies. That's where they have a spherical central bulge. And the lower one is like the barred spiral galaxies. Now in this particular video I'm not really touching on the bar because the bars are in the center. I'm more referring to the top branch. We have the spherical bulge, and in the middle you can actually get like intermediates which are kind of a weak bar. Now the Milky Way is on the bottom branch, so that's actually a barred spiral galaxy. Now some key things about spiral galaxies, this is again, it's kind of general, not always 100% true, but they typically have gas in. As they age, obviously that gas gets depleted and actually forms into stars. They have young blue stars because they have gas to form those younger stars. So they have a population of younger blue stars. As they age, again, actually they do get a bit redder. So they don't have quite as many young blue stars. They have disk-like dynamics. So they're kind of flattened and they're rotating like a disk. We then have our elliptical galaxies. These are more spherical in shape, and depending on their actual shape, they'll have a classification, so like E0 to E7, although like E7, they're probably not an elliptical galaxy, they're more likely a lenticular, but that's a different video entirely. And they're smooth, so they don't have spiral arms or anything like that, although there can be some features, but as a general rule, they're quite smooth, and they're mostly classified by their shape on the left-hand side of this Hubble classification tuning fork. So some key things about ellipticals: they have no star formation. Again, actually this is not technically true. They have quite low levels of star formation to no star formation, and the reason for that is they have no to little gas. So they can have a little bit of gas, but they have significantly less than a spiral galaxy, so their star formation rates are significantly less. Because of that, you have an older population of stars because you're not forming those younger blue stars. So the whole population of stars in these galaxies is older, which makes them redder. So elliptical galaxies in general are typically redder. So they don't have the gas, and the motions of the stars are more random-like. So they have a high, what we would call velocity dispersion, as opposed to more disk-like dynamics where they're kind of rotating as a disk. These are not really, I mean some of them do, they do have some net rotation to them, but generally their random motions are more dominant than their rotational motions essentially. So they're the two key things about those two types of galaxy. Spiral galaxies generally evolve into elliptical galaxies. Now they can do that through merging, or they can actually do it in isolation as well, but generally spirals are going to be younger than an elliptical galaxy. That's kind of like the end point, so they typically evolve into those. Now At the centre of galaxies, you typically have a bulge. Now these are higher density regions, they're brighter. I've highlighted a spiral galaxy here, but it's actually got a bar in. Imagine that's actually, we're talking about the actual spherical central bulge, really. And that's kind of what it's called, essentially. And they are, well, some of them are more spherical, some of them are not. So, two main types. We have the classical bulge and we have the pseudobulge. And they're going to appear in different sorts of galaxies, potentially, and they have different properties. So if we were to probe the inner part of these galaxies, we'd find the central bulge would have different properties. Now, classical bulges, these are generally kind of spherical. They are composed of older, redder stars. So they have an older population of stars there. And half of that is because they don't really have any gas and any new star formation. So they're kind of depleted of gas. And because of that, they can't form new stars. That then means you have an older red population of stars. The motion of the stars is more random-like. So they're not rotating as a whole unit, or like, they don't have a net rotation, basically. They are moving more randomly. So they have random motions of stars, high, what we would call velocity dispersion. And the light distribution from centre to outer part can be quite smooth. So they don't have any spiral arms, any rings, things like that. They're kind of smooth in the way that the light is distributed through them. And maybe that's made you think, well, okay, that sounds a bit like an elliptical galaxy. And you're kind of right. So classical bulges are kind of like mini elliptical galaxies. They share some similar properties. You know, they have older populations of stars. They have higher random motions of the stars. Hardly any gas star formation, that sort of thing. So they're kind of like a smaller version. And shape-wise, again, they're fairly similar in shape. Then you have your pseudobulges. Now these ones are actually disc-like. And what that means is you have a net rotation. The stars in them are kind of rotating around more like a disc, so there's a net rotation to these bulges, which the classical bulges don't have. They typically have younger populations of stars, so they would appear bluer. So you've got those younger blue stars there. And the reason for that is they do have gas content in them, and they do have recent and current star formation occurring, which is then allowing you to actually get those younger blue stars. So overall, a pseudobulge is going to be bluer than a classical bulge. And they can have spiral arms and other features like that, so that they wouldn't typically have a smooth light distribution compared to the classical bulge. And again, you can think of these pseudobulges as like mini spiral galaxies. They share similar properties. They've got disc-like dynamics, younger blue stars, gas content, star formation, that sort of thing. So they, in some ways, are like mini versions of that in the centre part of the galaxy because of the properties that they kind of share. Now, interestingly, you can actually get both types of bulge coexisting in the same galaxy in the centre. Can be somewhat rare, but you can actually get the same existing in the same sort of place, which is kind of interesting and raises some interesting questions as to how galaxies actually form. Why are you going to get both bulges in the same place? Because they're likely due to how they actually form. Maybe they've had a merger with another smaller galaxy that's worked its way into the centre. Maybe that's what's give rise to this coexisting bulges, essentially. Now, just to finish with an example here. So this is a classical bulge, and you're looking edge on at a kind of disc-like galaxy, and you can see in the centre part that it's more spherical-like. The disc is quite flat, which extends further out, but then the actual central bulge is spherical, and you can see it extending vertically because we're looking edge on here. So thank you for watching, and if you enjoy the videos and find them helpful, then do consider becoming a member. We have extra videos in the member section, but it also helps support the channel as well. So thank you for watching.